All right, that's hearing me. Test. All right, testing. I don't. All right, let's change this. Hopefully much better. This thing is crashing. All right. I think it's working, it's just not.
Recording in progress.
That happened. That means it went up. Okay, sorry about that. None. All right, let's get our class in. Good. Copy link. Nice. Get the chat up. All right, chat is up. Okay, can everybody hear me out there? Just say yes, no. All right, perfect, nice. All right, so somehow my laptop is not running fast as I thought it would be. Some issues. All right, let's resume. Any questions on VLANs? Yes, no, good. All right, so we'll continue to reach. Yeah. Right, so we now start to reach a point of VLAN tagging concepts. So this is, remember, we have a case of, we have two separate, now let me go back a bit. So as you can see that we actually have, VLAN 10, it's tagging it, so it's actually using one link and that tagging frame, one header frame, VLAN frame. So that, let's say that this belongs to that VLAN. When you switch on the other side, it receives that frame, that frame is going to actually look at the VLAN header, the ID, and see if there's any VLAN information. And there is one. It's going to identify which ports belong in that VLAN, and if there is any, send that frame to those ports. That's what's going to happen. And that's essentially what's going to happen. If there's no VLAN, matching what's in that frame, it would not send it to those ports. It will either, if there's none at all that is in this switch, it will just drop that frame because there is no VLAN of matching in this header. But in this case, we have VLAN 10, and we're going across. Right, so that frame is passed so that we will flood frame only onto VLAN 10 and not onto VLAN 20. And when it's the one in like VLAN 10 is like any ports that belong to that VLAN 10. So there's none then, so just going to not flood. Right, it adds as again, headed to the original Ethernet frame. Listen to VLAN 10 in this case. See if I can get my pen with the mouse, alright. Right, not only that, it switch to then removes the VLAN header forwarded. the original frame to the interfaces in VLAN 10. So what's going to happen here, your PCs do not have to worry about any VLAN tagging. The switch will do all the work. It will actually remove this header. So all the PC get is just a frame. When we start to do packet tracer, the interesting thing about packet tracer is that along the network between a switch to another switch or switch between switches, we can actually inspect the frame and actually see what VLAN numbers there is inside of it, which is good. So that's the advantage of packet tracer. If we had written GNS3, it had to be like a port sniffing or Wireshark, which is a little more difficult. So that's why I like the packet tracer for that purpose. One, right. Right, so now we look at something called 8221Q. So, and ISL VLAN trunking protocol. So what's happening is that what you saw in a previous few slides, you'll notice that there was something. There's a case of one link here. There's a one physical link with multiple VLANs being sent across, but we need to find out how to determine how to send all this across. It's not just a single link, it's a specially configured link, and that's where we call it a trunk link. And it uses a IEEE 8221Q protocol, or before it used to be called IS, the switch link with Cisco. Cisco created this protocol first, and then IEEE took it and created as extended and uses 8221Q. So now 8221Q is kind of like the standard, it is the standard, and eventually ISL VLAN, which is Cisco, that has become deprecated and they stop using it. I think if they now want us to just try in Cisco and they try to use ISL, it doesn't exist. Took it up. Right, so they over the years, so they supported two. Alright, so one is inter-switch link, that is Cisco's own, and this is IEEE. So this is Cisco, so that belongs to Cisco, and the other one is IEEE. So long before, right? Because it didn't, because of this, IEEE did not create or define trunking protocol. So imagine that this networking company ended up creating this first, and then IEEE followed up. So that's why Cisco became a big player in the internet world, because they were kind of leading edge out of protocols and technologies, even IGRP, which we'll do later on, of course, right? So they built those technologies. They're still a big player, but they can't lose that market share because let's say their technology, the one thing they can do is build bigger switches in a way, and network technologies that can do, it's there, but it's not as powerful, and other vendors are able to compete much faster. So I think the IT world really reached a point where it's very easy for vendors to start competing technology. They have the R&D, just like Intel and AMD, which is for microprocessors, ARM processors, Qualcomm, all these guys. So the realm really reached a point where there's big players coming out, and there's not one single person kind of owning technologies. Look at even cloud services. The big players in cloud is Microsoft, Amazon, Oracle. Who's the next big player? In terms of services and stuff. Who is it? Sorry. Google? Right, so Google, there you go. So there's four big players, and there's a nice thing to read about something called a Jedi contract where the United States Department of Defense, all that. That's some years ago. Right, so that's what's happening. It becomes more popular than the Cisco protocol. Why? Because of the standard. That's the problem. When standards start to come on board and becomes more popular, just like TCP became popular, everybody can support it, and that's why everybody can use different products, can use the same protocol, and they can communicate. Same thing with trunking, different products can work together and communicate using the 8221Q. So, like say my home network, as I mentioned on Monday, that I have three different vendor devices. I have Ubiquiti, I have Cisco, I have Netgear, and once they support this protocol, I can set up trunk in between all of them and use the same VLAN tagging if I need to. So I can do that. In this network, the same thing. We're doing testing with this network is Cisco predominantly. The wireless is now going across the 14 different vendor and products. But we're testing Huawei equipment on the network, we're testing 14 equipment, and they're all working interoperable. In that case, we wouldn't have all the fancy features and bells and whistles that every vendor like to sell or pitch their product, but at least we could get functionality in network with different products, maybe cheaper, depending on the price. And it changes. Sometimes some vendors will get cheaper this year, and in the next few years, the other ones get cheaper. So price will always go up. It's just whoever's low at that point in time. You guys know the benefit is. right? This circuit is quick. So this is where the 8-1 tag is inside the frame. You don't have to go too much in detail. You'll just, when you start to break it down, I think when you start to deal with span tree protocol, you will get more familiar with this 4096 and stuff like that. Because this will tell you how much VLANs that this is basically how much VLANs that this standard can support. 4,000 VLANs. But we only go up to about less than 1,000, maybe VLAN 1,000 or something like that. That's the most. There's extended VLANs beyond that, but we don't go more all the way up to 4,000. So anybody who's going up to so much VLANs is not, well, their design is not really going to meet what it's supposed to be. It's supposed to change up design. You should only need about maybe a few hundred, that's it. No matter how big your network is, you're supposed to be able to work with a small amount of VLANs, so you don't need so much. So you have the tag, private flag, the VLAN ID, and the reason why it's 4096, it's 12 bits. 2 to the power 12 is 4096, and that's where your limit is. When you start to talk about span tree protocol and bridge IDs and stuff like that, they will start to use per VLAN span tree. We're going to start seeing that the VLAN numbers are going to actually calculate into the span tree values. And when we will see it, then they actually calculate it. So we'll see how that goes. Right, so to break the range, the two ranges, normal range and extended range, as I mentioned before. Right, as extended. Again, so the normal range is right, 1 to 1,005. I think up to 1,001, 2, 3. Those are reserved for special purposes of Cisco, so you don't really see that being used. So maybe up to VLAN like 999, which you could use, but after that, there's a reserve, so you don't use it for that purpose. And of course, the VLAN information is still VLAN.dat. As I mentioned Monday, the VLAN.dat is one of the files that saves information about the switch. So the two files you have to erase is running the startup config, sorry, to erase. And then you have the VLAN.dat file to erase if you want to really clear the configuration. Right? Some use extended VLAN IDs from 1006 to 4094, but we don't really go that far. Even this network, we only use up to about 107, I think, as I mentioned before. So we don't even reach enough 500, for instance. Right? Now, what happens here? So there's one VLAN, and this is important to know. There's one VLAN that does not have tag frames. Now, it defaults to use VLAN 1. So VLAN 1, let me go back. So let's say we have VLAN 10, 20, 30, 40, etc. They will all have a tag happening with a VLAN ID in this. But when there's one VLAN, in this case defaulted to VLAN 1, and you could change it, where it does not have any VLAN ID in this, and there's no tag frames. Why am I saying that? Is that if you put a device on a port that is a native VLAN port of VLAN 1, that device will have access to all whatever it is on that VLAN. Right? So if it's on tap port, that's the problem. And this is the next problem. So yes, it does not support understand trunking, but based on design, we do not do this. In my lab, when you do the lab, I'll go into more detail, I'll explain it here. We do not put devices on the native VLAN. As a matter of fact, the native VLAN or with tag frames is something that we put that as a DMZ VLAN, a VLAN that nobody will have access to. So if by mistake an equipment cover that it plugged into, that device will not have access to the network. It's limited, it's restricted. Right? So that's the problem. We really have to be careful with this. I would like to go into more detail about it, but that's more security problem can end up more security issue if I go into more detail. So just remember, untagged frames is where you're plugging a port, that's it. But at the end of the day, and that's the thing. Let me just write down something here. Right? This untagged frame stuff is normally seen on a trunk port, is where you'll see untagged frames. Well, yeah, hold on. Let me just put trunk port here. Right? So, and when we go through configuration, you'll see the trunk port where all the VLAN tags are going across. There's a frame that's untagged, that's the untagged VLAN, that's the default. That'll happen on trunk port. When you configure switch ports with access, and it's actually on a VLAN, that's necessarily untagged free, the switch strip is out the VLAN ID VLAN tag. So when you're thinking, hey, I'm plugging my PC and it's working, you see that, hey, it's a tag free port. No, it's not that. The switch actually removes the VLAN ID header and then passes the traffic that leaves the regular frame out to the PC. So the PC doesn't need to know if it's on a VLAN or not, right? So that's what's happening. But just remember, in most cases, on tab frames, when we start to talk about that, you deal with something called a trunk port, and we'll deal with that just now. Right, so LAN switches receive layer 2. It's a layer 2 concept. All this is layer 2. The concept of VLAN as broadcast domains, remember I mentioned VLAN are separate, so that's really a broadcast domain. And as I go into the lab, when I do the lab Saturday, I'm going to demonstrate how we're going to take our existing shadow network and start to split that up into the true broadcast domain it's supposed to be. Because right now, when I did the lab last week, I showed you that we had the shadow network and that's IPv6 was set up, and then when we were trying to do default set up default gateway and let DHCP pick it up, it was picking up two sets of IPv6 on it. It was picking up the regular network and it was picking up the shadow network IPv6, which means that yes, even though the IP address, IPv6 address is separate subnets, the broadcasts, they're seeing, both of them are seeing the broadcasts, and we need to use VLANs to separate these broadcasts. So that's what this lab is going to do. This weekend, we're going to actually start separating these broadcasts to make sure that only the shadow network has its own broadcast, and then the student network has its own broadcast. And we're going to see that. Right, routing. So I'm just going to mention routing. You will see routing in the lab, but we're not going to touch routing. The focus of this lab and this week will be showing how to separate your broadcast domains with VLANs. How you're going to get the data to communicate between those networks. I'm going to do that in the next week, week 5. Right, into more detail. So that's routing. But I'll just show you in this example here. Let me see. Right. So when I include VLANs in a campus LAN, the devices need to be in the same subnet. In different VLANs, in the different subnets, what we should know is that a switch will not forward packets. In this example, this switch would not send packets between VLAN 10 to VLAN 20. You basically literally separate the switch into two different components in this case, two different switches. And that's what I like about buying. You're buying a good switch that managed, that you can separate into VLANs. You could buy a 24 port and then break it up into like 5 ports is for this VLAN, and next 5 ports another VLAN, 2 ports another VLAN. So you separate the different networks. So the next question is, well, how do you get those networks to communicate? Well, that's where routers come in. You'll use routers. So that's what we're going to demonstrate that next week with routing and inter VLAN routing at the same time. So that's the cool thing about it. So that's what we're going to do next week. But I'm going to show you how to, right now, the lab is going to show you how to split up the networks. Get our shadow network separate from our student network. I'm throwing in additional networks to make it more complicated. Just to give you an example of how we can have people in one area physically, but they're in a different network. And the VLAN is going to help us with that. Right, so network as a whole, we support traffic flowing into and out. So how do we do this? Yes, of course, we must. So if you have to get packets between two different broadcast domains, you have to use a router to move packets between one to the other. That's what you have to use. That's the answer in this case, routing packets between VLANs, and we'll talk about it later. So this example here, routing, in order for this to work, and I demonstrated that in the IPv4 example. When we did the IPv4 setup, I had one PC configured with 2 IP addresses on 2 interfaces, and each interface was set up with one network on the shadow network and one on the student network. And that PC now pinned with both networks because there are 2 interfaces, one on each network or each subnet. So essentially that's what the PC is from. It closed the router. It has not done routing yet because it cannot move traffic and send it between the PC and the same boot. Right? So in this case, take the next level where the router device will be able to send traffic between the 2 networks in this case. So it kind of links it up. Now you ask yourself, well, what was the point of doing this in the first place? So the shadow network, and that is why I did the lab with the shadow and student network, was that they would actually share on the switch at the same time. There were different subnets, but on the same switch, and yet the switch was sending broadcasts to both sides. So your switch is learning MAC addresses from both of them, and then the devices are learning information about the others, right? That is what we don't want. We want to send the switches split, and that's what's happening. What we want to do the right way is to be able to send traffic from one network through the router to the next network. And one advantage of that, yes, you reduce broadcast traffic between them, but you also can manage how you want to send traffic through. You can actually block traffic flow and prevent one network from accessing the other when you're applying something called access control lists. That's later on as in the WAN course. Right, I wouldn't go into too much of this. This is where it'll go through the router and stuff. Just go through the router and stuff. Right, so this case here, and this is hopefully we'll do that next week when we start routing, is that we'll do a simplistic way of routing where we actually, and that's what this one is, where we actually have two physical cables, one coming from one VLAN and then one coming from the next VLAN. That's what we will actually demonstrate. That'll be next week. Right now, when you look at the lab, you're going to see a router, and then you're going to see two cables. It might be reflecting what is going to happen, but it will be a little different. So I might put another router in, we'll use that, and then we'll go back to the other one. Right, so what is shown here is that if we keep using every single VLAN, you need a separate interface to connect to that router. If you have 5 VLANs on that switch, you need to have 5 interfaces on that router, one to each interface port on the switch. Problem is that you're going to need 5 ports on that router, and you're going to need 5 ports on that switch. That's just to get 5 VLANs to communicate with one another. So because of that, the study say, well, is there a better way to do this? And it's because the fact that we can actually tag and put a trunk port and all that and have everything on one cable, can we do that to a router? So basically, yes, you can. You can actually have one cable from the switch to the router, just like how we have one cable between two switches, and you can pass all the VLAN traffic over it. That is what this example does. You can actually pass all the VLAN traffic from the switch to the router. This is what they call inter-VLAN routing on a more or less router on a stick, because it's one cable coming out, router on a stick they call it. And you could put any amount of VLANs on this switch, and then your router could route between any of those VLANs. But the trick is, how do we tell the router, hey, there's one cable coming in? How do we tell the router that there's each one to identify all the different VLANs? Right? You have to use something called sub-interfaces, and in sub-interfaces, you have to use something called A221Q encapsulation as well. So you have to start to do encapsulate the frames into like layer 3 stuff. So you kind of have to end up dealing with some advanced encapsulation, but once you know the commands, it's easy. You just have to understand how to run the commands. And you'll be able to get encapsulation working on the interfaces and sub-interfaces. So we'll see that. When I put out the lab, it'll actually have, right, so routing packets between this term. Routing between VLANs is shorthand for routing layer 2 packets between layer 3 subnets, with those subnets each mapping to a layer 2 VLAN. So the question is why? Right, so it's just, you can't route, well, in terms of routing between VLANs layer 2, the router is basically taking traffic from one network, so one broadcast domain, and you're sending traffic to another broadcast domain. Right, and that's basically where routing will come in. So we just say routing between VLANs. That's the shorthand, but it's really between two broadcast domains that we're going to use routing. So that's a better term, routing between broadcast domains. So I was questioning why. Right, let me, I'll skip through all of this because I'll come back. I might most likely come back to this next week. So I'll just go through this because I want to go into VLAN configurations in the next slides, right? So this is something with a layer 3 switch. We will deal with layer 3 switches later on in the course. And I'll show you how we could use a layer 3 switch is basically, remember layer 1 is physical, layer 2 is basically MAC and deal with MAC addresses and frames, and layer 3 is basically packets. So a switch that deals with layer 3 is basically a switch that can actually deal with packets. Means that it can actually manipulate packets, deal with it can actually route packets. Which is good because you have more ports in a layer 3 switch. That's why we like to use layer 3 switches for that purpose, because you have 24 ports or 48 ports, and each one can be a routed port to send traffic out to a different switch or different network. So it gives us more capability. Right? Let me just go back. One caveat, disadvantage of routing on a stick, all traffic flow is limited to the bandwidth of this link, physical link. So if it's a 100 meg link, all traffic flow is 100 meg. Therefore, traffic coming in here 100 and going back out will be 100. If you have a gigabit link, that's the same thing. Traffic coming in is gig and traffic going back out is going to be gig. If you have multiple PCs copying data to PCs on the other side, they're all going to be limited by this gigabit link. You're going to have each of them copying separately. You might get each of them only get like 500 megabits of data transfer because it's going to balance off half. Some might be a little more. You might get 400, 450 in one. The other might be about 550 or the other one, depending, right? Because it's going to balance out. The link is going to be saturated. Now you're limited. It's not the full gig that you have, right? So, but now campus network we have. How is this uplink to? So most of us are gig. No, sorry. This building is uplink class 100 meg, but that uplinks to a distribution switch, which is uplink as to the core, which is 10 gig. So technically, once you bypass this 100 meg limitation, you have about maybe a gig. You can have a gig routing capability between devices or 10 gig for our network. I think we have. I think we go up to 20 because we have two sets of links between equipment. So we could route. Is that?
10 gig speeds.
Yeah. Well, we could route at 10 gig speeds. It's not. That's old. That's set up like years ago, since 2012. So now we need to upgrade that. So then the next step after 10 will be like 40 gig, then 100 gig is the next link after that. But I'm seeing 40 gig now, like in the next 4 years, and after that, the next 10 years might be 100 gig routed, be better. But yeah, so that's the time frame I'm seeing. But we'll see how the demand goes and how traffic flows and all the needs, because most of the needs for this campus is really internet. So how much you could buy for the bandwidth right now. So that might be more expensive. Right, so that's why the gig is enough. Or 10 gig is more than enough in most requirements. Right, so that's the problem with into VLAN routing. There's saturation of the link when you're passing traffic between it. Me personally, that's why I don't like it. But you just have to end up working with it and do that. Right, I'm just wrapping up this piece. Right, imagine a switch configured with 3 VLANs. How many IP subnets are required, assuming that all hosts and all VLANs want to use TCP/IP? Right, so 3 configured VLANs. Right, how many subnets, IP subnets? Anybody online saying anything? Nobody said anything online? No? Alright, well, answer will be 3. It's obvious because each subnet is its own broadcast, is basically subnet will match our broadcast domain. So there are 3 VLANs, there are 3 broadcast domains, and each broadcast domain must have its own IP subnet. So you could work it back that way. 3 configured VLANs, that's 3 broadcast domains. Each broadcast domain must have its own subnet, IP subnet. Right? And this is the key word here, is when they're saying IP subnets, right? So this can be a /24 network at 22, it can be at 25, at 26, 27. It could be it could be 3/27 networks. And all will look like 192.168.1. Well, there could be 1.75 and 1.100 or something, right? It could be 3 of those. All those are different IP subnets. What makes it different is all of them have a different. The mask is what's going to make the subnet size. Determine the subnet size, and again, the mask is going to determine if you're in the same subnet or not. But remember, you're working from layer 2 first, broadcast domains first, and then the subnet to broadcast domain. That's really calculating it. Right, so you have to start from that given this network. If you build it from scratch, you could plan with IP subnets first. So you can say, okay, I want to have 1,000 computers here. This level on the side note is that we have over 5,000 connected wireless devices on this network, right? So I'm going to ask the question is, what is the subnet size for that to accommodate 5,000 devices? Sorry? 5,000. How much devices is that? What is the subnet size for that? Google it. We could work with a base case, right? Let's try something here. We can start with basics. So a /24 network is 256. We work with 256. Each time we go up a bit and make it smaller, /23, you double in the size, right? So we're going up to the next level, will be a /23, and that's 512. Going up again, /22, right? That's 1024. So we hit 30,000 now, which is good. Next one is /21. Sorry, erase that. Right, a /21 is basically 2048. A /20, looking good, should be 4096. Oh, sorry, 4096. Quick question, is this greater than or less than 5,000? Less than, right? So we'll have to go next step again, we'll double that. Right, next step is a /19. Right, that is going to give you 8192. That's the subnet size we have to design right now. So we hit our limit. That's it, that's literally there. We hit the limit. Now we have to go louder. Right? And at this point, we are not using our 192.168 network because we already used it up for our main network. So we'll have to use a class B or class B network, which is 172.60/19. Or to be safe, we'll do it as a /80 because we're not so sure. We'll double that to 16,000 since we kind of supposed to have 16,000 students in the campus. But why we have 4,000 or 5,000 is because of students and staff. It adds up. We have about 2,000 staff, and the rest will make up students. So it's not as much as you think, but so that's I'll tell you. So like I said, when you're doing subnet design, this is the example of a subnet design happening here. We had our requirements. We exceeded the requirement. We exceeded it right now. So we went beyond the requirement. So we have to deal with expansion. So that's what we have. We only build on subnets. We have to cater for, okay, how much people they expect to be in this network for the next, sometimes we say 5 years, sometimes we say 10 years. Problem is that this is designed for 10 years. It's not enough. So we thought 2000 wasn't enough. That wasn't enough. We actually have to change the design again. Right? So keep growing. So we will have to plan ahead and say, okay, sometimes the expansion is more than we thought. So for fixed areas like a building where we have offices, that's easy to work. We can say, okay, you only have about 500 people or 200 people, we're not expecting any more because they can't fit more offices in there. Wireless is where the problem starts because it becomes nebulous. You come into class here, right now we have about my laptop, your phone, my phone, I have 2 phones here, so I already have 3 devices connected. 3 IP, 1, 2, 3, 4, 5, 6. 6 plus 3, I already have 9 IP addresses just already taken in this room. Right? And that's not counting that you guys may have a tablet or so, an iPad for instance or something. That's another additional. So we could double that. Right? So 9 back to 18 already, that's this room. We have the next room down the road. What if we fill this room up with over 100 students? That's 100 plus by 1.2, so we get like over 120 or 100 and something, 150 IP addresses that you guys are connected. See how fast this 4,000 can reach? Right, this is classroom. What about TLC? Right? You have C1 is bigger. C1 is almost 200. Here again, about 100. So that's just this block. Then you have 113, 114. And then you have TCB1, you have TCB2, TCB3. That adds up. And that's just here. Then you have engineering. So you see how easy it is just for everybody. Adds up, right? This is the beat in the room. So that's why you have to plan out your network, and that's what you do. right command reference. So let me go on to the next slide quick. I think the next slides will deal with configuration. Wow. Yeah, this is, I don't know why it is slow. So every device I use doesn't just dies. I have to really optimize these things. Right, so look at, this is basically configuration, trunk ports. This piece I wouldn't touch much on into VLAN routing yet. We can deal with that afterwards. Next week, that's where we're going to focus on routing. And then we look at VLAN tracking protocol, VTP. VTP is more Cisco, well, not really Cisco, it's more Cisco thing, but in most cases we don't really need to use it anymore, but we still keep it. That's into the end, this is VLAN 22. Choose two answers, which is following. Alright, well, let me not go into this because you guys can really have question and the answer, right? So the answer I think most likely be is exists. No, so these things, so the answer might be AB. That's what happens. Yeah, AB. This process, you can actually create a VLAN by entering VLAN 22, it'll create a VLAN in the database. So this is going to create it. So this is raw runtime. It doesn't exist in that situation, at least one interface assigned to that VLAN. That's not correct. You can actually have the VLAN exist, but without any interfaces assigned to that VLAN. And you can even put it on the trunk. Like I mentioned earlier on, you can actually pass traffic to it, but there's no VLAN, there's no switch port configured. It will take the VLAN information will come in to the switch. It's just that there's no ports to forward it to, so it'll just discard the frame at that point. Right, but so that could happen. So yes, you're going to be show VLAN brief will show it, and then you should run the config because this is done at the switch when you're configuring. It's only running config. It would because you did not do save now. Your startup config would not have this. So if you save the information, then it will be in startup. But if you should say check your startup config, it wouldn't be there. All this is in RAM at this point. Right, but the switch must be configured to believe that I like that one. Right, to believe that a VLAN exists. Right, switch must have non-trunking interfaces called access interfaces. So that's the next thing. So you realize something called non-trunking. So a particular VLAN. So if it's a trunking interface, it'll just pass the traffic through. It's just passing traffic. It doesn't really care about where there's go. It just passes that traffic. Right. So if there's only when you have an interface where you plug a PC in, and when it becomes non-trunking or access port, then we assign VLAN and trunkless ports. The last set of slides, I think it's 434, we'll talk about something called a voice VLAN. So this is where this will not really apply so well. We'll see that later. Right, to configure, you actually type, you go into global configuration mode, you type the VLAN ID command, and from there you're going to have VLAN ID configuration mode, you type name, and the name of the VLAN. If you don't type name, if it's not configured, the VLAN will automatically call itself VLAN 0ZZ, which is our 4-digit number, right? It's the 4-digit decimal for VLAN ID. So it can actually be, if you do VLAN 10, it will end up being VLAN 0010, right? That's how it will end up going because the max size is 4,000, right? So that's four digits. So it doesn't have to go more than that. And I will, of course, I recommend you name the VLANs based on the purpose. I think there's a certain limit of VLAN number size. The letters can be up to about, I think, 20 characters for the VLAN name. So you should just try to be very short on the VLAN name as well. Once you create VLAN, what you're going to do, you're going to assign an interface, or assign VLAN, to that interface. Right, so you pick select an interface type number, which we would have right. So we have not touched this. We have not touched interface stuff yet in switching. Right. All we're just doing in this so far we've reached was IP address configuring PCs, connecting equipment together, and then watching broadcast storms going on broadcast going across different networks. Now we reach a point of really hitting the CLI command interface of a switch, where we're going to do this configuration. Right, so we're actually going to go into an interface, and we're actually going to configure and assign a VLAN ID to that port. Right, switch port access, VLAN ID number command, and then mode access interface. Sorry, hold on. Right, switch port access VLAN. And I always put this mode, switch port mode access, to tell the port to actually go into access mode. This port can actually switch between access mode and trunk mode, which we don't want. Well, naturally, Cisco has that feature, but for our environment, for security, we don't do that. We don't want a switch to go from an access mode port, right, where you're plugging a PC, to a trunk port, where it actually can pick up VLANs from frames from everywhere. Because that's a security issue. Imagine you have a device that pretends to be a switch, right? And it's actually picking up frames from other networks, right? So that's the thing. Because it picks up frames from other networks means that I can pick up frames from a server network. I can pick up frames from a network that leaves with payroll network. I can actually pick up frames and actually try to start to do spoofing of IP addresses and stuff like that. And then I need to do man-in-mail attack, and then that's how you get into the network. So that's why we try to secure the network. No matrix access, so there's only that information going to reach that switch. Right, so this is our layer 1 switch, and we have 3 VLANs set up. In the lab, we will have, I just try to see top of my head, I think 1, 2, yeah. So in the lab, we'll have a few switches will be configured where we'll have 3 VLANs set up. All the ports into that VLAN, but it doesn't have a route. All the ports into that VLAN, but it doesn't have a route now to go anywhere else. So that stays and nothing, no traffic could pass through it. Right, we don't want to have default VLANs set up. Right, so you notice, and that's what, look what happened here. Alright, so you see these guys here? Or this is default, this is actually coded to the equipment. So all these different types of VLANs for those purposes, that's why we can't use it. Right, 1002, 3, 4, and 5. That's why we can start from 1006 and up, or 1001 is the most you could use. So that's like VLAN 999 or 1000, that is in max. Right, so this, as you can see, the VLANs above do not exist yet. The default VLAN 1 is there. Let me show you VLAN 1, that's the number here, right? 1. 1 exists as the default. So now we have to create. So then you go into configuration mode, and then you start typing the VLAN number here. So that's VLAN 2. Go straight into VLAN configuration, and then you actually type name Fred's VLAN. In this case, it's Fred's VLAN. Exit, and then what you're going to do, interface range. And this is, I mentioned before that you can select a range of interfaces, and then you're going to put switchboard access VLAN 2. You put them on Fred's VLAN. Of course, for security, we'll put switchboard mode access, and then M. So that will be assigned. The next slide should show you, right? Well, they do show running config, but the other command is, so it's 2 things. So they did a show running config. Alright, that's this. So they did a show running config, and the left show running parts. Essentially, the running config only has the literal commands that you type is actually here. Fred 2, name Fred's VLAN, that's it. That's in the running config. So the switch, when it boots up and it loads the running config, the startup config. Well, this once it's saved, it becomes the startup config. But when the switch boots up, the cool thing about it is that it boots up and you start to execute all these commands that you have put in there. Now, technically, you can take your startup config or running config and take the commands out of that and copy it and paste it in your terminal, and it's supposed to set up the equipment with the right settings. Technically, in most cases, it would not work because there are certain points where it needs to wait for the switch to give you a response or to go the next step. There's some things like SSH cryptographic keys that will be in the startup config or running config, but you can't type that in the terminal. That is generated by the system. So there's certain things that will be generated that you cannot type on the command line. So because of that difference, what I would recommend to you, and that's what I will do in the course too, I will have a text file with outlining all the commands required to do your configurations. So when you finish this configuration, you're going to have a text file with something called enable configure terminal VLAN2, name Fred's VLAN, then interface range, switch port access VLAN2, and that's what this piece is. So this here, and this block of text, and the next block of text, well, all of these two will be in one single text file. I can highlight that, copy it, and paste into my terminal, and it will execute an integration VLANs for me, right? So that is what I would recommend you do, because, and let me tell you, if you doesn't want to like coding, you're doing your code, and you have your scripts, bash scripts. You could copy it and paste it into the command line, CLI. You all did bash scripts before, right? Bash program, CMD, use a different right. So you can actually, basically the bash file is a whole list of commands in there. So you're basically creating a command file for the Cisco commands. The only problem is that you can't just tell the Cisco equipment to come out and execute the file. You just have to copy it and paste it in the terminal. So that's the caveat right now. But there are advanced Cisco settings with Python, Python, and using Ansible and all these things to man the switches remotely. They will take the command file and pass it to the switch and execute it. So that's what they can do. But all you know is body text file. Right. Show VLAN brief. So you want to know, hey, what is the switch? So this is the thing. The information that you typed above here is the commands that you know. The problem is that, all right, I'll have to leave now. There are people who are waiting for next class. I'll just, no, not yet. I have 3 minutes. Well, 1 actually, but I'll take it 3. So the thing about it is that these are the commands you type, but to really see the switch is actually working how you want it, you have to use the other commands to view what it did. So you do show VLAN brief, and it's showing the default one to, well, there, but I'm supposed to go to the next, right, there you go. And that's what you're going to see, another item here showing VLAN, the Fred's VLAN, and it's active. So only there is when you actually see, hey, did it work? Yes, you have to use these commands to know if it did work or not. And that's the reason why you have to go back and forth. One, to see what your config commands you type, what is the running config, plus what the switch is actually telling you. Because it's important to know that when you start going routing and BIGRP later on, you're going to say, hey, I typed this command. Why am I not seeing the effect? And then from your knowledge, you have to know, hey, the ports could be off, disabled, the routing protocol is not running, and that's the reason why you're not seeing it, right? So that's why you need to do both. Know what the commands are you use, it's in the system, and then what is the end results of it. Right? Show VLAN ID 2. Well, they went straight into there, and you see Fred's VLAN there, and I think that covers that piece. Let me see if I could finish it off. Right. Show the VLAN configuration. Right. So before we show how we created the VLAN first, this is showing me how we can actually create the VLAN while we are in the interface configuration. So this is a shorter way. Not really recommended because you're going to get a default VLAN number coming up, which is, you could change it later, that's fine. But if you build out the configuration, you might as well do the right steps, right? So this is configure, you're going to configure terminal, interface range, this is the range here. Switch port access VLAN tree, it didn't exist before, you type it in. It creates it one time and assigns ports to that VLAN and end. That's basically up to here. From this, these just basically 2 lines, and that's it, because you're already, this global config and this is the end. So you technically at this point, it'll create the VLAN and assign it in these 2 commands here. Right? One is to select the ports, and the other one is to this assign it and create the VLAN at the same time. So that's VLAN tree happening here. And you show a VLAN brief, and that's what you got. Right? So if the VLAN wasn't created before, the switch will automatically create it, and the default name of 0003, and that's what will happen. If you want to change this, there is, you're going to, okay, no, sorry, that's the end of that. If you want to change it, you just have to go to config mode, VLAN tree, name, and then the name of the VLAN. Call it Barney's VLAN or something like that, and that's how you're going to name. And that's what's going to happen. Right? For me personally, I would normally put the VLAN number in front and then the name of it, because I can see in one column all the details about the VLAN, the number and the name. Here now I have to rely on 2 columns. So that's my preference. That's all. You don't have to do that. You could just put the name there. Right, so that's the end. Which of the following are membership models most supported by VLANs? Choose 2. Public, private, static, dynamic. This should have been in the next slide because that's on the other side. But the answer is either static or dynamic because when I type switch port mode access, that's static. But if I don't type any commands, it's going to be dynamic. It means it's going to be between access port or trunk port. And again, we don't want dynamic, so we don't want this. This is part of something called DTP as well. Dynamic trunket protocol. Most cases we take this off. We don't want this on. We don't want it to go from trunking to access. Right? So let me just finish that. Configure commands you can check. And it is a summary here. So that's 4.3.2. Right. Right. So let me finish off here. You guys can read up the last slides if you want. And I'll see you guys on Saturday for the lab. I'll push up the lab maybe today or Friday, depending on Saturday. Take a look at go through the lab and see how it goes, right? All right, thank you. Oh, attendance. You guys did attendance? Oh, back up here. Thank you very much. All right, everybody in Zoom land, see you. Bye, everybody. All right, so bye.